Hey kids, Mr. Murray here. We're back and we're doing a few more examples of U-substitution today. This time focusing on some trig examples. So let's see how they're essentially the same strategy that you take with the non-trig problems, but sometimes they can get a little trickier. So same idea here. We're trying to integrate this, and you see it's not just a simple sine of x or sine of 2x even. It's the sine of 4x to the fifth minus 7. So that's a classic candidate for U-substitution. And like always, that classic first strategy, that go-to is let the inner expression be U. So U is going to equal 4x to the fifth minus 7. And now, so here's where I'm at so far, right? And I've got to get that dx to cancel along with that x to the fourth. Can't have it. It's got to all be in terms of U, or whatever variable you're integrating with respect to. So here's the du step that kind of makes it all click. So the derivative of each side, and on the right side you get 20x to the fourth dx, so that differential already split up. And you see you're trying to get rid of 10x to the fourth dx, and you practically have that right here. You've got the x to the fourth dx, but you've got 20. So if you're like me, you like to divide both sides by 2 and kind of say, hey, I'm going to be left with 1/2 du. That's what is equal to 10x to the fourth dx. So I can take out that 10x to the fourth dx and replace with 1/2 du. So here we go. The 1/2 can be out in front of the integral, or you can leave it in front of the sine function. And when you view it in that form, it's really a pretty simple antiderivative. Antiderivative of sine is negative cosine. Don't forget about that. So we have negative 1/2 cosine of u plus c. Don't forget about that plus c, because these are indefinite integrals. And then we just substitute back in. What was u representing? It was representing 4x to the fifth minus 7. So this is sort of our work off to the side. So it's negative 1/2 cosine of 4x to the fifth minus 7. If you want to check, take the derivative, and you should get right back what you started. Very easy to check, and you kind of see how that chain rule plays out and how it leaves you with something like this out in front. And that's all you're trying to undo with U-substitution. Just trying to sort out that chain rule that must have happened to get you to that point. All right, let's just see a couple other examples. Okay, so this time you've got two trig expressions, 4 sine of theta cosine squared of theta d theta. So on the inside of the two trigs, there's just theta. So it's not like there's an obvious thing like in the last problem, like 4x cubed on the inside. But you look at this exponent, that's cosine squared. That's the dead giveaway there. So when you have not just a basic trig function, but it's raised to an exponent, oftentimes, think about what that's really saying. That's really saying cosine of theta squared. Your inner expression in this problem is cosine of theta. That's what you want u to be. So u is going to be cosine of theta, and that means you're left with 4 sine of theta u squared d theta. And how is that sine of theta going to drop out? Well, that's the du step, right? So the du, if u is cosine, the du is negative sine of theta d theta. And you see, there it is, sine of theta d theta. So that mental step is, what should I let my u be? If you can think ahead and say, if you see its derivative kind of sitting there in the problem, you know you've picked a good u value, because when you do the du, the derivative step, that part's going to cancel out. So in this case, I'm looking to cancel sine of theta d theta. So that means when I do, I'm going to be left with negative du So that 4 is still going to be there, so you'll have negative 4 u squared d, whoops, d theta will be replaced with du. Okay, so integrating that is really kind of a piece of cake, just a simple power rule. It's just that u is standing in for a trig expression. So it becomes u cubed, you divide by 3, you have negative 4 thirds, u cubed plus c. And again, u is standing in for cosine, so that's really cosine cubed of theta with a negative 4 thirds out in front, right? Take its derivative if you want to check. 3 times that negative 4 thirds will leave you negative 4. Cosine squared, then you multiply by the derivative of cosine, negative sine. It's going to change and leave you with what we started with. Very nice. Okay, one more here. You've got the integral of 6 secant squared of y over the square root of tan y dy. So in this case, I would go and say I'm going to let u be tan of y, because that is, it's on the inside of the square root. And also I'm thinking ahead, saying, hey, what's the derivative of tangent secant squared? And I see secant squared kind of sitting right on top, so I know that will cancel out when I do my du step. So here we go. If u is tan y, du is secant squared of y dy. So I know secant squared y dy, that is all just equal to du. So this, I'm doing one big substitution. There's a 6 on top. All of that was replaced with du, and that is the square root of u in the bottom. And that's the sort of thing we've integrated 100 times. So that's really 6u to the negative 1/2. Add 1 to that exponent, u to the 1/2. Divide by 1/2, you multiply by 2, you get 12, u to the 1/2 plus c. So that's really 12, and if you like to make it square root, and u is tan of y. 12 square root of tan y plus c. Okay, so there's 3 different trig examples there. Hopefully that kind of gives you enough to think about. And if you have any questions, as always, feel free to ask. Keep working, kids.